Hi guys, I am back and I'm sorry that it took me so long to upload the video for chapter 26. I had like a very busy day until now. So for this week, I'm going to upload some lectures about chapter 26 and chapter 27. So it will be a little lengthier, but I'm not going to go through every section of the book. So I just selected some sections that I thought it is important for you to know. And because we lost the first week after the spring break, so we are like a little behind the time. But I mean, that was necessary. And I try my best to cover as much information as possible. But I will try to, set the priorities and just talk about the important material. The first topic that we're going to talk about is the reflection of the light. Okay, so the reflection of the light is changing the direction in which light travels. Now, the simplest way to change the direction of light is probably by reflection from a shiny surface. To make it easier for us to draw and talk about the light properties, let's just treat the lights to be rays. So what I'm going to use is that I show the light by an arrow. So this means that the light is traveling from left to the right. When light hits a surface, it reflects, or at least some of it will reflect. Now, the law that we're talking about here is the law of reflection. That tells us the angle of incidence, which I show by theta sub I, equals to the angle of reflection, which I show by theta sub F. And you remember that we talked about the normal to the surface. So this line is the normal to the surface. So the angle of incidence is the angle that the incidence ray of light makes with the normal of the surface, and the angle of reflection is the angle that the reflected ray makes with the normal to the surface. The next topic that we are going to talk about using the law of reflection is forming images with a plane mirror. We are all familiar with looking at ourselves in a mirror. Now, if the mirror is perfectly flat, that is a plane mirror, and then we see an upright image of ourselves as far behind the mirror as we are in the front of it. So if I show the plane mirror by this line here, and then I have an object, let's just put a flower. And this is exactly like the figure 2610 on your book. So let's have the nice object. So let's call the object, and please pay attention and learn the notation that I use here, because we're going to keep the same notation throughout this chapter and the next chapter when we talk about lenses, microscopes, telescopes, and all types of mirrors. So this is the P, which is my object, and then I know that in the plane mirror, the object is the same distance behind the mirror, and let's say this is behind the mirror, and in front of it we have the shiny surface. So this is P prime. So I show the object by P, I show the image by P prime, and then let's call the distance between the mirror and the object by D, which is distance sub O, which stands for the objects, and then the distance between the image and the mirror, let's show it by D, which stands for distance, sub I, which stands for the image. Now, in the plane mirror, what we know is that DO equals to DI. Okay, so this was the first example, the plane mirrors, and let's just look at the properties of mirror images produced by plane mirrors. The first property is that the image is upright but appears reversed right to left, and is something that you can test yourself. Just stand in front of the mirror and try to wink with your left eye, and your image winks with the right eye. The second property is that a mirror image appears to be the same distance behind the mirror that the object is in front of the mirror. And then I showed this by this simple equation here, that DI equals to DO. So the distance from the image to mirror equals to the distance from the object to the mirror. And the third property is that the image is the same size as the object, and this is something that all of us have experienced. Like when you stand in front of the plane mirror, you have the same size, of course. Let's go ahead and talk some about the spherical mirrors, and this is section 3 on your book. Now, another type of mirror that is encountered frequently in everyday life is the spherical mirror. So these mirrors, they get their name from the fact that they have the same shape as a section of a sphere. Now, if you look at figure 2615 on your book, it exactly shows how these mirrors are being shaped. So what happens is that a portion of a spherical shell of radius r is cut away from the rest of the shell. Okay, so if the outside of this spherical section is reflecting surface, then the result is a convex mirror. So convex mirror is the mirror that the outside of the spherical section is the reflecting surface. So the reflecting surface is here. Reflecting. Now, if it is opposite, if the inside surface is reflecting, so if it has this shape, so this is the back of the mirror, and here is the reflecting surface, then we call this a concave mirror. So no matter if the mirror is convex or concave, we always define two quantities to be ordered to see how the image is formed in these types of mirrors. Let's for now just consider a concave mirror. So this is the concave mirror. And then whenever I use these dashes, it means that this is the back of the mirror. So this is where the material to make the mirror like the back of the mirror not shiny, or cover the back of the mirror is placed. So the first quantity that we need to know is what we call the principal axis. So this is the principal axis. And then the next one is the center of curvature. So this is actually the center of that sphere where the mirror is taken from. So again, so the spherical mirrors are a part of a sphere, so they're taken from a full sphere. So this center of curvature that I show with C is the center of that sphere. So it's called the center of curvature. So the principal axis is a straight line drawn through the center of curvature, and the center of curvature is the center of the sphere with radius r, of which the mirror is a section. Now, the midpoint of the mirror is exactly the principal axis too. For the convex mirrors, we have the same the axis and the center of curvature, but of course, because this was a part of a bigger sphere, so when I draw the principal axis, the center of curvature should be behind the mirror, right? Because it is the center of the sphere where the mirror was taken from. So this is C, and this line is my principal axis, and then this is the reflecting surface. Now let's talk some about the focal point and the focal length in the mirrors. And I want you to look at your book at figure 2617. When we want to investigate the behavior of spherical mirrors, we need to suppose that a beam of light is directed toward either a convex or concave mirror along its principal axis. Now, let me draw this for you. So the first ray that is hitting our mirror is in the principal axis in this direction. So it just reflects back on itself. But then imagine that I have a beam of light that is going to hit my surface like this. So because here the surface is at this angle, it's gonna reflect back like this. And then if it hits here, then because this is my surface again, and it needs to go back with the same angle as it is incidence. Here again, I have a beam of light. So it might just consider that the beam of light is coming in the parallel form. So this is the initial beam of light, right? So they're coming in parallel with each other. And then here again, because this is curved, so I can say that this is my surface and this is my normal to the surface. So it is being reflected in that way. After reflecting from the mirror, the rays diverge as if they originated from a single point behind the mirror that we call the focal point. So they diverge, and this is going back in this direction. So they diverge as if I can draw this correctly, like this, right? If I have more beams, then you can see that they were diverge as if they were coming from this point behind the mirror, and this is what I call the focal point, and I show it by capital letter F. So this is the focal point. Now, focal length is the distance from the surface of the mirror to the focal point. So this distance between the focal point and the surface of the mirror, I show it by the small letter f. So that is the focal length. It appears that the focal length for a convex mirror of radius r, and so this the center of curvature, the distance between the center of curvature to the mirror is my r, right? So this is the radius of the original sphere where we took the mirror from. Now it appears that for the convex mirror, focal length is -½ r. Now, the minus sign in this expression is used to indicate that the focal point lies behind the mirror. So that is why we use the minus sign here. It appears that for a concave mirror, we have the same rule, but just with a positive sign. So focal length is still half of radius of the sphere, but with a positive sign. And I quickly try to draw a figure for you. So this is my concave mirror. This is the principal axis. And then imagine that the beam of light is coming, and let's call this to be C. And if the beam of light is coming in parallel with the principal axis, so again, because here, like this surface of the mirror is exactly like this, and the normal to surface is like this, so it kind of reflects in this direction. In the axis itself, it reflects back in the same direction. If it hits here, because it's more curved here, so the normal is more tilted, and then it reflects back and pass through this focal point here. So this is my surface, this is my normal to the surface, and same as this part of the mirror, if the beam hits it, then if this is my normal, then it reflects from this focal point. So this is my focal point, and you see that it is well, if I drew it nicely, it would be exactly the half of the radius. But it is positive sign again because the focal point now is in front of the mirror. Now let's talk some about ray tracing and the mirror equation. Ray tracing gives us the orientation of the image, the size of the image, and the location of the image in a spherical mirror. Now, the second method to give us like a relationship between the distance of the image regarding the distance of the object is called the mirror equation. So now let's start with the ray tracing at first. When we want to use ray tracing technique, usually we just take one ray that is the representative of the rays of light. Now I want you to look at figure 26.22 on your book, and we usually the simplest way is to use 3 rays with simple behavior that are used most often in ray tracing with spherical mirrors. Now I'm going ahead and tell you about these 3 rays more. So let's consider again a concave mirror, and then I have drawn the principal axis for you. And let's consider that this is the center of curvature, and then I know that the focal point is halfway through. Okay, so the first ray that I'm going to use is called the parallel ray. So if a beam of light is incident parallel to the principal axis, let's call it P, then it reflects through the focal point. So it reflects through a focal point. Now this is a rule. Okay, so the parallel reflects through the focal point. And it could be a little cleaner here. Now, we have the focal point F. So if a ray of light is incident through the focal point, then it reflects parallel to the axis. Then it reflects parallel to the axis. So let's call this, so this was the P ray, let's call this the F ray. And then the simplest one is what we call the C ray, or the center of curvature ray. Now anything that shines, let me continue this mirror so I can just like have an example for you. So anything that is incident through the center of curvature reflects back along its incoming path. So the ray that is incident through the center of curvature is just reflected back from the center of curvature. So these, and let me call this a C ray. Don't know why this looks like G here. Go ahead and correct it. So these are the typical three representative rays that we use for spherical mirrors just to be able to form an image. Okay, to see how these rays can be used to obtain an image, let's consider a convex mirror that is figure 2624 on your book. The first thing to do is always to draw the principal axis, always to specify the center of curvature, and always to point to the focal point here. Now let's just place an object, and we usually show the object by an arrow because we want to show the direction, if it is upward or it is reversed. So this is my object. Let's put it in front of the mirror. And I'm going to use the three rays that we talked about to just see how the image is formed. The difference between this mirror and the and the previous mirror is that here the images, here is the rays diverge from the mirror as if they had originated from the tip of the image from behind the mirror. So we have to take care of that in our drawing. The first ray that I'm drawing is the P ray. So this is the one that is parallel to the axis, right? Okay, so what happens here is that I know that the surface of the mirror is like this, and this is my normal to the surface. Now, in this type of mirror, what happens is that the ray reflects so that the continuum of the reflected ray passes through the focal point. So with the concave mirror, the P ray reflected through the focal point. In the convex one, it is reflected so that the continuum of the ray passes through the focal point. So it is going to reflect like this. And I don't know how I ended up to be such a bad drawer here, but it is like this, right? So the continuum of the ray is passing through the focal point. Okay, one thing that I forgot to tell you is that we always draw the rays from the tip of the object, not the bottom. Okay, so if you find a tip where the tip is, then it is easy to draw the image. Now the next ray is the F ray. So here in the picture above, and I'm talking about this picture here, so you see that the F ray is the ray that passes through the focal point and then it reflects parallel to the axis. Here, because the focal point is behind the mirror, I draw the ray as if the continuum of the ray would pass through the focal point. So if this is the continuum of the ray, so if the ray is incident at the mirror so that its continuum passes through the focal point, then it reflects parallel. So this is my F ray. The same is applied for the C ray. So if a ray is incident or shines at the mirror in a way that it passes through the center of curvature. So if I can draw this nicely. So if I have a ray that is going this way, then it is reflected back on itself or on its original path. Okay, now I have, and this is my C ray here. All right, now I have the three reflection. So I have this reflection for my P ray, I have this reflection for my F ray, and then I have this reflection for my C ray. Okay, now you see that they are just like getting away from each other, so there is no way that the image is formed. Image is formed when the rays are just like coming back together. So what I do is that I continue this reflection. So I continue this, and then I continue this. Now, because here I don't have the ability to choose different colors, it might be a little confusing for you, but if you take a look at your figure, the figure in your book, and then watch this video, it will make more sense. And then I continue the reflection. So what I'm doing here is now I'm continuing the reflections. I'm not continuing the incident beam. Okay, so this is important that you notice that for the image, you will be continuing the reflected beams, but when you are just tracing or when you're drawing the reflected beams, you will continue the incident beam. Okay, so this is where they hit. So this is the tip of my image. So the image should be somewhere here. So this is my image. Now you can see that this image is formed behind the mirror. Okay, so if this happens, we call this image to be a virtual image. The real images are the ones that are formed in front of the mirror, as we can see in the next example. So we can see from this diagram that this virtual image is upright. So the properties is that it is upright. It is smaller than the object, and it is located between the mirror and the focal point. So it is between mirror and focal point. Let's look at another example. That is example 26.5 that says use a ray diagram to find the location, size, and orientation of the image formed by a concave mirror when the object is between the mirror and the focal point. So like always, I draw the mirror, and this is a concave one. Then I show the center of curvature. I go ahead and show the focal point should be like half of the way. And then it tells me that the object is between the mirror and the focal point. So let me just place an object here. Now again, I'm using this is my object. So I'm using the three rays to figure out how the image looks like. Okay, so the first ray is the P ray. The P ray is incident parallel. So this is my P ray. And then I know that once it is parallel, then it is going to reflect through the focal point. So let me go ahead and reflect it through the focal point. Okay, the next one is the F ray. So the F ray should be incident on the mirror passing through the focal point. But how can it pass through the focal point? Because focal point is behind the object. So again, I use the continuous of the ray. So I draw a ray. This is my F ray, so that the continuum of the ray is passing through the focal point. Now, when this happens, then I know that it reflects parallel to the axis. So this is the reflection. Now, if you use different colors, it's just easier to see. And then the next one that I'm using is the C ray. So again, it's the same thing that is happening. So this is my one reflection, this is my second reflection, and then how can I just like have a beam that passes through C when C is behind the object? So it is again that simple. I draw a beam of light so that the continuum is passing through C. And I know if it is incident like this, it will reflect back from its original path, right? So this is my C ray. So this is my third reflection. Now, you see that they're just like getting away from each other. So this cannot form an image. So what I'm going to do is that I'm going to continue the reflection. So this is the continue of the first reflection. This is the continue of the second reflection. Continue until they reach each other. And this is the continuum of the third reflection. So they hit here. Nice. Now I have my image. Well, it seems that image is bigger. Wow, so the image is bigger, it is upright, and it is virtual. So I have a virtual image because it is behind the mirror again, which is upright, and it is bigger than the object. Nice. Now, before we continue to know the equations of mirror, I want you to go ahead and look at table 26.1 for the imaging characteristics of convex and concave spherical mirrors. Now, I want you to actually go ahead and figure out and draw the object location for every case that is given in the table. For example, the concave mirror object location beyond C, C between F and C, just beyond F, just inside F, and this and that. Now, if you draw all of them using these three ray tracers, then you have the better feeling of how the image is formed. The mirror equation is a mathematical relationship between the object distance and the image distance for a given mirror. Now, I'm not going to like prove and derive the equation for you. It's just like as simple as we know that 1 over dO plus 1 over di equals to 1 over f. Okay, so this is the famous mirror equation. dO is the distance of object to mirror, di is the distance of image to the mirror, and f is our focal length. And of course, we need to recall that f is half of the radius. That is important too. Now, we need to take care of some rules when we apply this mirror equation. Okay, let's start with the di, the distance of image to the mirror. So this is positive if I have real images, and it is negative if I have virtual images, which means that the image is in the back of the mirror. Now for the object distance, dO, this is positive for the objects that are in front of the mirror. So real objects that are in front of the mirror. And it is negative for virtual objects, and that is true. We have even virtual objects. So if they are behind the mirror, if the object is behind the mirror, then DO is going to be negative, or we put it as negative into the equation. And the last equation that I want you to pay attention to is the magnification of the mirror. Magnification that I show by M. Now, magnification is the ratio of the height of the image to the height of the object. Okay, so M is the height of the image divided by height of the object. Or I can write it to be negative image distance over object distance. So this shows if my image is bigger or smaller than the object. And then another rule that we have is for the focal length, and maybe I just should go back and add it here. So for the focal length, we have it positive for concave mirrors, because again, it's going to be in front. And then I have it negative for convex mirrors. Okay, knowing this information, let's go ahead and solve a problem. Exercise 26.8 says the convex mirror in figure 26.24. I am trying to look at the figure 26.24. Okay. Has a 20 centimeters radius of curvature. So I'm dealing with a convex mirror. So just like quickly have it in mind that it looks like this. And then I have C here and then F here. So just right away, I can say that because the focal point is behind the mirror, F should be negative, right? So this is what we talked about. Okay, so the radius is given to be 20 centimeters. Find the image distance. Find the image distance for this mirror when the object distance is 6.33 centimeters. Okay, now we need to recall that focal length, because I use this curved F for frequency, let me just use the straight one. So F is half R, and here it is negative because again the focal point is behind the mirror. So I can say that F is negative 10 centimeters. And the good thing about the mirror problems is you do not need to convert the units, because basically the equation is just the distances. And if everything is in centimeter, then you get the numbers in centimeters. Okay, so now I know my F, and then I know that 1 over dO plus 1 over dI equals to 1 over F. Okay, so I have the D object to be 6.33, and it says that the object is like positive 6.33 centimeters. So I assume that it is in front of the mirror, so it is positive. So I just go ahead and put 1 over 6.33 plus 1 over DI equals to negative 1 over 10 centimeters. So I just can go ahead and find DI to be minus 1 over 6.33. And then eventually when you calculate it for DI, you get negative 3.88 centimeters, and boom, it appears to be negative. So it tells you that the image is behind the mirror and it is closer than the object to the mirror. So if this is the object, and you can go back to figure 2624 and check this fact. So if this is 6.33, then the object is going to be somewhere here because it is negative, but it is 3.88 centimeters away. Now, if you want to find the magnification, because now, I mean, we have drawn the rays, but according to equation, if you want to find the magnification, then it is just as simple as to write m equals to negative di to do. So it is negative 3.88 divided by 6.33. So it is positive. Let me go ahead and calculate this. Okay, so it's going to be 0.61, and this is another fact that is proven by this equation. So first of all, it is positive, so it means that the image is upright. So positive magnification. So if my magnification here is positive, that means that the image is upright image. Now, if it is negative, then it means that I have inverted image, right? So this is positive, so it means that it is inverted, and it is less than 1. So this tells me that the image is smaller. Sorry, I don't know why I did that, because here I have the 3.88, so it means that I have an image that is smaller and it is upright. And this example brings us to the end of this lecture, because so I have been talking for 42 minutes, so it's going to be like a big file. But again, I want you to try like all the possible scenarios for the location of the object in concave and convex mirrors, and find the location and the size and the direction of the image. I hope that you enjoyed this. So I'll be back on Friday with a new lecture for section 5 and to the rest of the chapter and some of the sections from chapter 27. Well, take care of yourself, and like always, please email me if you have any question, any confusion. Absolutely feel free to email me, and I try to respond you in less than a